I'm here to tell you about an upgrade that we've made to VIRGA v2.0, which is looking at how fractal aggregates affect the atmospheres of exoplanets. But I've been told by my colleagues that I should lean into my Christmas theme title, so it's actually now called Love Fractually, and that's because I realized that aggregate clouds are all around. So let's begin with some basic context. We know a lot about how clouds and aerosol particles behave from our own atmosphere. So the particles that we have can have a dramatic effect on things like the temperature and the climate of Earth. And there are lots of different processes that produce solid and liquid matter. So a few of those examples are wildfires, fossil fuels, and volcanoes. And all of these different things can inject matter into our atmosphere. Once it's there, the solid and liquid matter in the air can absorb or reflect light, and that changes the balance of energy that we receive from the sun. So, from all the radiation that hits us, about 24% of that radiation is immediately reflected by clouds, and then a further 23% is absorbed by the atmosphere. And zooming in, we can actually see some of these effects in real life. So, 2 years ago, there were some wildfires in Canada, which sent this orange plume of hydrocarbons all over the east coast of America. And this completely transformed places like the typical Manhattan skyline view that you'd usually see with kind of clear into the distance, suddenly became an orange haze. And so, this is a visually striking example of how these particles can completely change the opacity of the atmosphere that they're in. There are measurable effects that they can have as well. So after Mount Pinatubo's eruption in 91, there was a huge increase in the amount of sulfates in the atmosphere, and that actually had a global average reduction temperature of zero point 0.5 degrees, which is absolutely massive. If you look at the kind of climate targets we're looking to meet, that is a big difference as a global average. And you can measure in the data as well that the next 2 years following that were the coldest years from the last 35 that we've had. So we know that these small particles in our atmosphere can have big effects, but what about in other places? Well, we've observed that places like Titan, which have similarly thick hydrocarbon layers of cloud and haze, which dominate the upper atmosphere to that photo in Manhattan. So the entire thing ends up with this orange glow, but they're even more extreme there. It's like that Manhattan photo on steroids. And we expect most detected exoplanets to have some sort of aerosols in their atmospheres. In some cases, the abundances could be much more significant than they are on Earth. So we can actually detect these in the spectra using JWST. We've detected, for example, silicon dioxide clouds, which are effectively quartz in the upper atmosphere of WASP-17b. So how do we actually detect these? Well, they can impact the spectra because of their opacity and cause extra absorption features. So when we measure these wavelength-dependent opacities as a function of transit depth, I'm just going to zoom in on this because there's quite a few different models here, but the two that I want you to focus on are the model which is in yellow, which is a model with no silicon dioxide clouds, and the data points are in black. And you can see that they basically follow this pattern up until this point where there's suddenly a bump, which is not captured in the model without the silicon dioxide clouds. But if you include it in your modeling, then you can match that feature, and suddenly you can start to characterize these atmospheres with detections of specific constrained molecular features that explain what chemistry is happening and what particles are in the upper atmosphere. So how are these models actually behaving? What are we actually doing? Also, one more thing. So to figure out the atmospheric composition and structure, we put models like Picasso and Virga to data from the telescopes. And what are these models actually doing? Well, to start with, a lot of them are quite simple. So there's a few different options on the market, and most of these models assume that all particles are spherical. It's a good approximation if we are not sure exactly what we're looking at, and also it makes the calculations simple. But actually, in reality, if we look at the aerosol particles we have on Earth, they are definitely not spherical. They look like bunches of grapes. And the mathematical framework that we use to describe these is we call them fractal aggregates. But they are quite far from spheres. And I've spent a lot of my PhD trying to understand, well, what's different then? If we model these particles more accurately, how does that change the inferences that we're making? And if you model these particles more accurately, in some cases they can be up to 1,000 times more absorptive than they would be versus a spherical case. And that's for exactly the same amount of mass. If you just unwrap your mass into a slightly different shape, it can become extremely more absorptive. And so it's really important to capture these effects in the models that we're trying to use to get inferences from data. And so what are we actually looking for in the models? Well, light can either be absorbed or scattered by an object in all these different cases. And so we can work out the area of light that's absorbed and the area of light that's scattered. And if you add those together, we call that extinction. So that's the total amount of light that would be removed from an incoming beam of parallel light. And this was actually the first bit that captured my imagination with these models because they don't behave intuitively at all. You'd think from parallel light hitting this little sphere that the most amount of light you could ever block would be equal to just your cross-sectional area of your sphere. But even for a simple spherical shape, that's not the case. You can actually end up absorbing and removing from your beam way, way, way larger shadows, if you like. And that doesn't make sense if you look at it in terms of geometric optics. But as you guys know, when you have wavelengths and particle sizes that are similar, you end up with diffraction and interference, and waves stop behaving the way that intuition says they should. And so even calculating the optical properties is challenging in this one, and I've written two papers about different ways that we can do it quickly. But in this talk, primarily, I'm going to talk about what happens when we put these models actually into the clouds. So how do we actually model clouds? Well, I've started with a simple example. Here's Earth, and here's an ocean. And we're going to begin with some water vapor that's just at the surface of the ocean. Maybe a little wave broke, and we've got some water vapor floating around there. So heat from our sun or a star can make that packet of vapor rise. So it'll convect, it'll go upwards, get colder as it rises, the temperature decreases, and eventually it'll get cold enough to condense out into a cloud. And that's our basic cloud model. Now, what's really cool is that in that position, we have this upwards velocity to moving this packet of vapor upwards, and we get that from something called the eddy diffusion coefficient, which is kZz. And we know that for a stable cloud, then it can't continue moving upwards. There's got to be a balance force downwards, which comes from its terminal velocity. And that's going to depend on how big the particle is. So if you assume that this particle is in equilibrium and it's stopped moving around inside the cloud, these two things have to be equal. What that means is that you can solve for particle size. You can work out what size of particle, how big does my particle need to be to have a downwards velocity that's going to equal this upwards convective velocity. That's the point where it's going to stay stationary. And so we can split our cloud into 40 or 60 different layers. We can stratify it, and then in each of these layers, we can work out how big the particles are going to be. And that's important because we need that to work out how big their cross sections are going to be and how much light they're going to absorb. So it's really, really important to know the particle sizes. In reality, all the particles aren't the same size. So if you look at stratocumulus clouds in California, for example, there are actually a bimodal distribution that kind of characterizes how big the particles are. And that happens because you have growth, you have particles that have more and more condensation happening and the droplets are getting bigger. When they get big enough, they fall down, they hit other ones, and there's also fragmentation. And so you have different modes that are dominating. But what we can do to make our model capture those effects more accurately is just put a single log normal distribution over both of those two different modes. And that means that basically once we've found our mean particle size, we can then plot a log normal distribution about that particle size, and we capture those effects from having a distribution of small particles and big particles in each of these different layers individually. But the mean particle size in each layer will be different, and so the distribution will be slightly different as well. And once we've done that, we've got a cloud. We know exactly which pressures it's starting to condense at. We have this cloud structure going upwards, and we now know the particle sizes in each one, which means we can find the optical properties for each of those particle sizes. And finally, we can chuck some rays of light through it, which is really boiling down, very oversimplifying exactly what a radiative transfer code does. But that's effectively what we're doing. We're putting light through that atmosphere with the clouds involved as well, and we can suddenly start to see exactly how much opacity they're going to contribute to your transit depth and start comparing that to data. So I wanted to basically run through the changes that we've made. We have allowed VIRGA, rather than predicting spheres, like I said, a lot of the times the particles are these much, much more complicated shapes. So we've added into the VIRGA cloud code a way to model all of these 5 shapes on the left. There's a range of different what's called fractal dimensions, which parameterize the shape of the particle. So the fractal dimension is just a number between 1 and 3. 1 would be a straight line, and 3 would be a very, very compact object close to a sphere. And so just by assigning each of these different shapes a number, you can chuck these particles into VIRGA now. So this is some code that you might have used previously if you were trying to set up a cloud. You basically tell it what is the condensate species. So we've got some magnesium silicates. This is your optical property files. You set a sedimentation velocity, a metallicity, a mean molecular weight for the atmosphere, and then also the width of that log normal distribution. So this is how VIRGA ran up until version 1. And the changes we made are really, really easy to implement. You basically now just turn on aggregates. You set the fractal dimension, you say which of these shapes you want to run in your model. And then finally, there's a third parameter, which is how many monomers they have, which is the number of these little spheres that you want in your model. And so there's more detail in the paper about how to kind of pick those numbers, but that's how easy it is. There's just 3 extra variables that you chuck into VIRGA now, and you can see the impact of the shape type on the spectra. And there are a few extra diagnostic tools that we've added into it as well. So this feature lets you look at how much extinction happens as a function of particle shape, wavelength, and also particle size. And there are some other features as well. This one shows you how to find the radius in each of these different models. So how big are the particles that each of these models are predicting, and then also how many of the particles. And so I wanted to just give you a preview, a quick taster of the kind of things that you can do in VIRGA now. I'll link to the tutorial at the end if you want to know more. But what have we actually found so far? Well, if you basically just take a simple example, we've got 3 particles here that have exactly the same amount of mass, and therefore they have the same what's called compact radius. So if you screwed them into a ball, all those balls would be indistinguishable apart from their color. But what happens when you put this into a full cloud model is that the terminal velocity of the elongated aggregates on the left is much lower than the spheres. And it's simply because they have more air resistance, so they're going to fall slower. And so when we put this into our model, we've got some parameterized upwards velocity that's happening from convection, but the ones on the left would have a downwards velocity that's smaller than the one on the right because of that air resistance. And so because in VIRGA it's solving for particle size based on that upwards velocity, what it finds is that if you have an elongated aggregate, the aggregate is going to be larger, it's going to need to be bigger to exist in the same layer as the small spheres. So the big consequence that happens dynamically is that in a given pressure layer, when we run aggregates in VIRGA, these aggregate particles therefore have a much higher mass than spheres. They are larger particles, not just in shape, but also more massive particles as well. And so what consequence does that have when you run a full cloud? Well, the aggregates form into more massive particles than spheres. So the more you decrease fractal dimension, the bigger these particles become. These are obviously not to scale. They're not like, meters long, but they also form into fewer particles. And the reason for that is because the way that VIRGA calculates how many particles form, it depends how much mass of vapor you have. So you have this mass mixing ratio, and you look at the saturation vapor pressures, and it tells you how much is going to condense out, but that's agnostic of shape type. And what that means is that the same amount of total mass is going to condense out no matter how you model the shape. And so if these particles are bigger, because you have to conserve mass, you also have to have fewer of them. So we have these 2 quite different models now. We've got a model of clouds where we have very long particles that form into quite big chains, and then you have particles which are very, very, very small spheres. And both of those optically are going to behave quite different when you shine light through them and try to work out their opacity. So let's look at a few examples. This is an example of a hot Jupiter where we might expect magnesium silicate aggregates to form. And this is the kind of spectra you get. So there are small differences depending on the shape type. But what's really cool is that there seems to be a trend. So the dark blue ones are the most compact shapes, and then we've also got the light blue ones being the elongated ones. And so for this particular KZZ value, what we found is that the clouds made of the elongated particles have the highest opacity. Having few particles but big particles and elongated chains, those are the cases where we had the biggest transit depth. But if you change KZZ, just making it an order of magnitude bigger, which if you haven't used KZZ before, that's actually very common. Typically, papers will span 4 to 6 orders of magnitude with this number. So we make it a single order of magnitude bigger, and actually a really interesting thing happens. Suddenly the pattern flips upside down. And now the compact particles, the large numbers, but smaller particles and compact ones, suddenly these ones have the highest overall opacity. So it's interesting that this pattern suddenly flips upside down. But this is explainable. So the overall opacity in any of these cases is given by a parameter called kappa, and that's basically the number of particles you have times their extinction efficiency, which is how much light they're removing. It's linked to that extinction cross-section, times their area, their cross-sectional area, pi r squared, and then divided by m. We usually mass weight it. In this case, we're just going to ignore the m because they're all the same mass. But in each of these different models, we said that the number of particles was different. So first of all, let's look at how that's behaving. If you start with the same total mass, but you break some sphere into lots of different particles, then if you start with the volume of the sphere on the left, and then you've got n particles, each with a smaller volume on the right, the behavior of breaking a big thing into little things is that the number of particles will be inversely proportional to r cubes. So the smaller you make the particles, the more particles you're going to have. And that's typical behavior that we expect. What about Qx? Well, the extinction efficiency, the amount of light that's going to be absorbed plus scattered, that actually depends strongly on the particle size. And there are different regimes here. So for small particles, and 10 to the minus 4 microns is like the size of atoms. So this is going right from as small as is physically possible up to kind of micron size and beyond. For really, really small particles, the extinction efficiency is proportional to r to the power of 4, very similar to the Rayleigh scattering law, which is famous for making the sky blue. And then for the largest particles, then actually Qx becomes constant. And there's this bit in the middle where you have these kind of resonance features, especially for spheres. You get these nice little patterns. I can talk more about this later if you like, but effectively, I just want to focus on these two different regimes. Small particles, it behaves to r to the power of 4, and large particles, it's constant. And so what that means, oh, sorry, is that if kzz is higher, what are we actually changing in those two models? Well, if kzz is higher, the upwards velocities are going to be bigger, and so the particles are also going to need to be larger to stay in that same layer because they're being pushed upwards more. You're going to need a more massive particle to be pushing downwards with your terminal velocity to stay stable. And so in those two spectra in the last page, we had a low kzz where the particles are kind of small and a high kzz, and all that did, the only change that was made fundamentally is that the particles now have to be bigger to match that larger upwards velocity. And so we can have particles in these two size regimes, and that's going to depend on which Qx value we use. So in the low kzz case, like we said, both the particles are quite small. The aggregates are still bigger than the spheres. Because of that decrease in the terminal velocity, we still need to make the aggregates larger than the spheres to exist in that same pressure layer, but both of them in this kind of low kzz regime where Qx is behaving like this. And then in the high kzz case, we're increasing the size of our particles. Both of these different shape types get pushed out into this high kzz and constant Qx regime. But in both cases, like I said, the aggregates are going to be bigger than the spheres. And so mathematically, let's see how that behaves then. So for our low kzz case, let's take kappa. We now have all the information we need to work out how this is going to behave. We've got our n, which is r to the minus 3. We've got qx, which is r to the power of 4. And then we've also got an r squared. So if you collect together all of those r terms, 4 plus 2 is 6, minus 3, we end up with kappa being proportional to r to the power of 3. And so what that means is that if you make a particle bigger, if it has a larger compact radius, then your opacity is going to be bigger as well. And lo and behold, that's exactly what we saw. In the lower kzz case, the aggregates were bigger than the spheres. And so if they're bigger, they have a bigger compact radius, therefore they have a bigger opacity. And that's exactly what you see in your transit depth. What about for the high kzz case? Well, in this case, everything's the same apart from qx. So qx is constant in this case. And so when we collect the r terms, we've still got the r to the minus 3 from the n, we've still got the r squared at the end, but this term's constant. And so in this case, kappa is going to be proportional to 1 over r. And what that means is that the larger particle, which is the aggregates, is now going to decrease the overall opacity. When we put it in this model and we actually calculate the number of particles, take into account the entire cloud, it turns out that the elongated aggregates, because they're bigger, actually end up decreasing the transit depth versus the compact shapes. And so this toy model effectively describes exactly why we get this flipping, this inverted behavior happening when you change KZZ. It's basically changing the particle size, pushing it into the other regime. And one thing you might be thinking is, well, okay, does that mean there's a transition point where they're kind of the same? And one thing I did for the paper that was released last Friday is basically allowed a slidable interactive version of this plot to show you that happening. So if we increase KZZ, you can actually see this pattern flipping. And initially, where the elongated aggregates were the most opaque, suddenly now they're the least opaque. And you can plot this alongside particle size as well. So this is going to be small particles. And then suddenly, as the particles get bigger, eventually that pattern flips upside down. And there's some other cool things you can do with this as well. We've got a sedimentation parameter as well. You can see how that changes things too. But yeah, definitely check out the paper. There's a link to these spectra if you want to play with those as well. Cool. So we did this in a warm Neptune environment, a hot Jupiter, and a brown dwarf. I won't go into the other two environments because I'm running out of time here, but if you have any questions about them, please let me know. And I'll leave you with my key takeaways, which is that particle shape can cause measurable differences in spectra. You can see that there's some pretty chunky differences between these. And so particle shape should be considered as a free parameter in models. It's something that can significantly change things, especially in the short wavelength area of these spectra. And a third key point is that VIRGA 2.0 is now released, and you've seen how super easy it is to use just a couple of three extra variables to chuck in there, and suddenly you can see the effects of particle shape on any of the current models you've run. And we got some tutorials up there too, which I will link here. So there's paper one, which is the methodology and the benchmarking and all the work that Sarah Moran and I did to actually implement this into VIRGA. Paper two is the impacts, so the stuff I was just talking about there with the interactive spectra in hot Jupiters, warm Neptunes, and brown dwarfs. And then finally, there's a link to the tutorials if you're interested as well. Thank you very much.
Fantastic. Thank you very much, Matt. Really interesting stuff. I was going to ask if we have any questions, but it looks like we've already got two. So let's start with Anna.
Hi, Matt. Wonderful talk. I was wanting to start with a mean question. So, you never, or I missed your monomer sizes and how much you have played around with those, and have you ever been worried about actual crystallization and the shapes of crystals in your monomers messing with you?
Yeah, good questions. So monomer sizes is a parameter that you can change as well. So where I put a number of monomers into that VIRGA code in the mini tutorial, you can also set monomer size. And so in the first paper, we did three different monomer sizes in comparison to a benchmark study done by Kazumasa Ono, and then compared it to the microphysics code using different monomer sizes in their case as well. So yeah, you can either fix the number of monomers as 1,000 and scale your aggregate as it gets bigger or smaller, or you can actually fix the monomer sizes. And whilst we've explored that a bit, I would love for people to explore it further. So yeah, that's the monomer size. In terms of crystal structure, no. So we have looked at one refractive index profile for magnesium silicates and potassium chlorides, and this is very much like the first introductory paper on it, but polymorphs in particular is something that we want to do for some silicates in brown dwarfs. So yeah, that's coming, but not yet.
And Tad.
Yeah, this is a fantastic talk, Matt. My question is related to how you showed that the aggregates, have greater extinction opacity. I guess there's this really neat recent paper by Elijah Mullins et al., the Silicate Sundogs paper, where they show that grain directionality might matter as the grains might be aligned with the flow. I'm wondering if for these aggregates, you might also expect the grain directionality to matter and whether that might also change the extinction opacity and in which direction you think that might go.
Yeah, I mean, that's a really good question because as well as the optics, that's going to affect the dynamics too, right? If you have this elongated aggregate, it's probably not going to fall like a piece of paper. It might orient itself in a particular direction. So directionality is something that I really want to explore. The optical theory that we're using as base for VIRGA v2.0 is modified mean field theory, which takes an average. So it uses orientational averages, but I'm also very familiar with DDA, and that does allow you to actually say, right, your particles line like this and calculate a very specific optical cross-section based on its alignment. So we have all the tools we need to do that, and I would love to do that study. But yeah, again, it's in the pipeline.
Like, yeah, I'm really excited.
Okay, I think we've got time for one more. Shay?
Hi, indeed, great talk. I wanted to ask if you know of any creative ideas to test those, to study those issues in the lab experimentally.
Yeah. So the cloud formation, for example.
I was thinking about the optical properties of the aggregate, but other questions as well. But I know that there are lab experiments, but this specific topic of the optical properties of the aggregates is very intriguing.
Yeah, yeah, absolutely. So there does certainly exist quite a few different labs that are making exoplanet analogs. So especially for things like the hydrocarbon hazes. And the way that we use their data in the models is they provide us with the refractive indices. So we use lab-derived refractive indices for things like hydrocarbon hazes. And then we can model, okay, what happens if you change the size of the particles? You can model it in that sense. Hopefully that answers your question. That's basically how we integrate it at the moment. In terms of like wider, like we use the theoretical models of how they behave dynamically from the lab studies as well. Both of those things have been done separately. So people look at how these aggregates fall and kind of sediment through liquids and the fluid dynamics. So that theoretical model is derived from lab studies, and then the optics as well. Yeah.
Okay, thank you.
Okay, we're at the top of the hour. So thank you very much, everyone. If you have any other questions for Matt or Morgan, then please do contact them. And we'll see you all in the new year.